We'll give the others 2 more minutes, class, ha? We'll wait for them. We'll start by 1:35.
You can a little bit more time to play.
2 p.m.
Okay.
Okay, class, good afternoon. We'll start with the prayer. Let me share my screen. Let me know if you can see my screen, okay? Saint John Baptist de la Salle, pray for us. Give Jesus in our hearts forever. In the name of the Father, and of the Son, and of the Holy Spirit. Amen. Afternoon, everyone.
Good afternoon, Miss.
Were you able to see the prayer video?
No, miss.
Wala, Miss.
Awa ay, umugin na siya perming, ginareklamo, hindi nila masi. Anyway, sige lang. I'll find ways to share the video to you later on. I will place it in the PowerPoint slide. Okay, so for this afternoon, we will continue where we ended with electrochemical and nuclear energy. That's our module number 3. Number 2. And we're done with balancing redox reaction. So I introduced already redox reaction last meeting, and I gave you something to work out as well. Okay, so for this afternoon, we will hopefully finish the entire module 2. That way, next week, we can start with a new topic. Okay, let me share my screen. Okay, wait, class, I think I was not able to open Canvas. Okay, so we go to your modules. And we're here on electrochemical and nuclear energy. And if you click the lesson topic, you'll be able to see the notes for this one. Okay, so we're here. Just a short review of what we have discussed last week. Can you all see my the page I'm on, the projected page on reduction and oxidation reactions? Can you see it?
Yes.
Okay, sige. Thank you. So, a review. So, what is it that tells you that the particular element is being reduced, and what is it that tells you that a particular element is being oxidized? So anyone who can share his recollection of what was shared last meeting, when can we say that a particular element was oxidized or it was reduced? So there's only 19 of you. Where are the rest? Anyway, 18 including myself. So that makes it 19. There are a lot of your classmates who are not able to attend now because some have power interruption, some have very bad weather from their end or at their end. So anyone who can tell me what's the difference between a reduction and an oxidation reaction? You can place it on the chat box. I can read it for you if you don't have a microphone. What's your recollection of a reduction or an oxidation reaction? Because last week, that's what we discussed. And we even ended with the balancing. We started with the determination of the oxidation states of the elements present in a particular compound or in the formula of a particular compound. Oxidation loses electrons. Reduction gains electrons, correct? So if an element loses electrons, it's said to be oxidized. And the reaction it is undergoing is said to be oxidation reaction. When a reaction accepts electrons, it is said to be reduced. And it's undergoing what we call reduction reaction. So as such, the pair of these two may occur simultaneously. So you have a case of a reduction oxidation reaction, or in short, redox reaction. So last meeting, we also learned how to balance redox reactions using half reactions method, whether in acidic or basic solution. Okay, I will not anymore enumerate the steps because I'm sure you have already practiced on how to balance redox reaction because that was your problem set. So for this afternoon, we go to a new topic. Let me increase this one so it will appear bigger. So we'll go to voltaic cells. So what are these voltaic cells, or otherwise known as galvanic cells? Okay, so when we speak of voltaic cells, the energy released in a spontaneous redox reactions can be used to perform electrical work. This task is the task of a voltaic or galvanic cell, a device in which the transfer of electron takes place through an external pathway. Later on, you will know what's the name of this external pathway, rather than directly between reactants present in the same vessel. So there is a corresponding amount of energy that is being released in a redox reaction. Last meeting, we discussed it. And this particular energy is used to perform electrical work. Now, where is the, shall I say, where is this redox reaction occurring, or what is the vessel that is being used to accommodate this particular redox reactions that will produce electrical energy or perform electrical work? So that particular task is done by our voltaic or galvanic cell. Okay, so in here we have the use of what we call an external pathway. So you will learn later what is this external pathway, so that the reaction that is occurring, reduction and oxidation reactions that are simultaneously occurring, will continue. It's something that is not stopping. It's something that is supposed to be as designed, something that will continuously perform what is said to perform, unless otherwise there are some parts of the electrodes that needs to be replaced anymore because they are worn out or depleted. Now, one such spontaneous reaction occurs when a strip of zinc, so let's say for example, you have this zinc metal in here, is placed in contact with a solution of copper. So you have this particular electrode of zinc metal is dipped into a solution of this particular metal as well. So ang solution, naging butangan mo sa zinc electrode, is also a solution of this metal, zinc. And in this particular reaction, you will have it connected with a copper. So as the reaction proceeds here, the blue color of the copper ion fades away, and the copper metal deposits on the zinc. So as you could see, the copper metal here deposits on the zinc because this one is connected to another electrode we call the copper electrode. You will see it later. So the copper metal deposits on the zinc. This is your copper actually that deposits on the zinc. At the same time as the copper deposits on the zinc begins to dissolve. These transformations shown in the figure below are summarized by the equation that you are seeing now. In the process, your zinc metal here is being oxidized. Why we say it's being oxidized? It's because it's giving away how many electrons in this case? It's giving away 2 electrons. You see this 2 plus in here? As a review again, whenever a neutrally charged atom loses an electron, it becomes positively charged. And the number of electrons it loses, or the number of electrons it loses or give away, is equivalent to the charge that you are seeing on this particular zinc cation now. So originally it's neutral, and now it became 2. So meaning it gave away 2 electrons. So we'd say that your zinc here is undergoing oxidation. It's being oxidized by what? It's being oxidized by copper, which is undergoing reduction. Why we say that copper is undergoing reduction? Because you could see here that originally copper has a +2 sign. If it's the one that accepts the 2 electrons that zinc gave away, it became neutral here. So the electron acceptor is your copper. And since it's the one that is accepting the electron that zinc gave away, it's being reduced. And the reduction agent is said to be the zinc. Now, if you look closely here, I'd like to zoom in. Why na siya i-zoom? So, if you look closely here, let me check class ha, if I can increase this. Oh, sorry. Okay, if you look closely here, you have the, this is your zinc. This is your zinc metal. And you have copper ions in solution. So this is your copper ion solution. So what happens is atoms in the zinc strip, by the way, class, sorry, this is the zinc strip. This is the zinc strip and this is your copper solution. Your zinc strip is being dipped into your copper solution. Okay? So what happens? The zinc metal gave away 2 electrons, as you can see here. Zinc, zero charge originally, that it became +2, so it gave away 2 electrons. The 2 electrons given away by zinc, this is your zinc metal, is absorbed by your copper solution. So your copper in the process accepts the 2 electrons that zinc gave away. So in the process, it became neutral. Originally, it's copper 2+. This could be probably copper nitrate solution. Oh, sorry, no, copper sulfate, because nitrate is -1. So this could be copper sulfate with a -2 and the sulfate and ion. So that will give you a copper 2 ions. Now, in the process, you could see that there will be more and more, as says here in the what we have read, there will be more and more copper. As reaction proceeds, the color of the copper fades away. So from dark to light. So darker di siya, naglighter siya. And then the copper metal deposits on the zinc. So you see this black thing here? That's the copper metal now depositing on the zinc. And what happens if the copper metal keeps on depositing on the zinc? The zinc begins to dissolve. So there are several things that are happening here. Let me annotate so we can take note of the things that are happening. Okay, wait class ha. I'll just get my pen. Okay, what happens here is this. So it's a spontaneous thing that happens. So the color blue of the copper fades. So this is the first thing that is observable. Then the copper metal deposits. And then the zinc begins to dissolve. If you look on the picture below, okay, I cannot. So these are the 3 things that happen. If you look at these things below here, the first thing that illustrates number 1 is this. Let me annotate. I will just scroll down later. From dark colored to light colored. Sorry. It's not, I should not be pointing to that. From light colored solution, from dark colored solution to light colored solution. So that's number 1. Then the deposition of the copper on the zinc metal. And the third is the solution of the zinc metal in solution. So these are the 3 things that happen in the simultaneous redox reaction that seems to be happening in here. Let me clear my drawings. Okay. That's a close-up view of what is happening. The zinc plus copper. So the zinc, this is your zinc metal here. And this is your copper solution. So the copper adheres on the zinc. Okay. So the blue, that is why from the dark blue to light blue. And then your zinc cation becomes plus copper now makes it The zinc 2 cation plus the copper now is the product of the reaction. So this is the initial thing that happened. These are your reactants and these are your products. So from this particular reaction, this is your reactant, original. This is the original state and this is now your product. The zinc 2 plus the copper, this is now the resulting scenario. Actually, do hindi niya siya parehos ng ibang reaction that you see a particular set of reactants and then after the reaction already happened, you set a different set of products. No, in this case, you can still see the part of the reactant here, which is your zinc metal. And you can still see here the solution. But the thing is, the property of your solution is different already. In here, your solution is darker. In here, it's lighter because of the deposition of the copper in the copper solution in here in your zinc metal. So what happens is, this is now your product and these are your reactants. So a simultaneous redox reaction. Now in here, the two solid metals are connected by an external circuit are called electrodes. So in here, you have a scenario wherein you have now the use of metals in solutions as what we call electrodes. Electrodes. Let me annotate. Your metals in solution are called the electrodes. So in the previous scenario I gave you, you only have one beaker and a metal on it. And your reaction is spontaneous. Both redox reactions happening in that one particular beaker with the metal zinc. The beaker contains the copper solution. Now in here, you have two beakers already. And in these two beakers, you have two solid metals. Now they will form the electrodes. We call this to the electrodes in our cell. We call this the galvanic cell. By definition, the electrode rather in which oxidation occurs is the anode. So oxidation, acceptance of losing of electrons happens in the anode. Losing of electrons. The electron at which reduction occurs happens in the cathode. The acceptance of the electrons. So this one is losing of electrons. Oxidation, this one is accepting of electrons, which is reduction. The electrons can be made of materials that participate in the reaction. As in the present example, over the course of the reaction, the zinc electrode gradually disappears and the copper electrode gains mass. More typically, the electrodes are made of conducting materials such as, so we don't limit it only to zinc and copper, but any conducting material, specifically a metal. Now, in this case that is stated here, we can use platinum or graphite. Now, this too does not gain or lose mass during the reaction, but serves as a surface at which electrons are transferred. So whenever you have already electrodes present here, you have already two beakers in here. Now, what you have is a case of metals that don't gain or lose mass. So your electrodes dipped in a solution in these two beakers does not gain or lose mass during the reaction. They only serve as a surface at which electrons are to be transferred to or from. So they don't lose or gain mass. Unlike if you have a standalone beaker and a metal placed inside it, which is dipped into the solution present in the beaker. So let me clear my drawings. Now, each compartment of a voltaic cell, this one is a voltaic cell, is called the half cell. We call this a half cell. This one is also a half cell. Okay, one half cell is the site of the oxidation half reaction, and the other site is the reduction half reaction. And as such, you will have again the occurrence of a simultaneous reduction oxidation reactions. Okay, so one is being oxidized, the other one is being reduced. Now, in our present example, zinc is oxidized. We know that because the zinc gives away its electrons from 0 charge to positive 2, and your copper is being reduced from copper 2 plus to copper only, which has a charge of 0. Okay, so anode. Anode is where your oxidation half reaction occurs, and cathode is where your reduction half reaction occurs. Take note of this. So the losing of electrons happens in the cathode, the gaining of electrons happens in the cathode. Now, electrons become available as zinc metal is oxidized at the anode. So, electrons become available. What do we mean by this? Electrons are present in solution because your zinc metal in the first place is being dipped into a solution. So, as your zinc metal is being oxidized, there are more and more electrons being made available in the solution. They flow through the external circuit to the cathode. So there is this mention again of an external circuit that allows these deposited electrons or electrons made available in the solution of the anode to transfer on the other side. And there is this what we call external circuit. Now, they are consumed as copper 2 is reduced. What does this mean? The metals that are available in your anode, they are made available because it's your zinc metal that gives these electrons away. So, di man siya makadto. Tsara, di siya sa iya solution sa anode. So, if this particular cell of yours, half cell anode, half cell anode where oxidation is happening, is connected to another half cell, which is the cathode, by means of an external circuit. The electrons made available in the solution in your anode is now transferred to the other side, where, as I mentioned here in the phrase, where they are consumed as copper 2 plus. So they are being used by copper so that, as you could see in here, the copper now becomes a neutrally charged element or atom. From positive 2, gingamit itong mga electrons na nag-transfer from the anode to that side where it is located to gain a 0 charge, from 2 plus to 0 charge. Now, because zinc is oxidized in the cell, the zinc electrode loses mass. So take note, because your zinc is being oxidized in the cell, the zinc electrode loses mass and the concentration of the zinc 2 plus solution increases as the cell operates. So maiban iya nga mass because ng more and more of the zinc gets deposited in solution. And the copper 2 solution becomes less concentrated. It becomes less concentrated. Why? Because your copper 2 plus cation is being converted to or reduced to copper. So as your zinc is oxidized, it loses mass in the anode, and the mass of the solution or the concentration of the zinc 2 plus solution increases. An increase in the zinc 2 plus solution results in a decrease in the concentration of the copper solution. Why is that? Kaya ang imo nga copper 2 plus nga cation, i-convert na siya sa zero charge copper or a neutrally charged copper. So that is why it's now converted into copper, not copper 2 plus. So this gains mass while the other one loses. So take note, the anode loses mass, the cathode gains mass. Now, for a voltaic cell to work, okay, nabla na mention ko nga dapat wala sang gain or losing of masses. So it's explained here. For the voltaic cell to work, the solutions in the two half cells must remain electrically neutral. As zinc is oxidized in the anode half cell, your zinc 2 plus ions enter the solution, meaning your zinc, this cation is now transferred into the solution where your zinc metal is dipped into, upsetting the initial zinc 2 plus and sulfate. So, tsakto ang hamba ko kaina, it must be zinc sulfate. Sulfate charge balance. So kay nagsulod ang zinc plus 2 nga cation sa solution sang anode where your zinc metal is placed into, what happens is ang balance ang charge balance is already disturbed. Hindi na siya neutral. Kaya mas nagdamo ang zinc 2+. So, hindi na siya neutral. How do we address this? Or how does the voltaic cell design work? That way, it will not continue to happen. The increase in the concentration of the zinc 2+ cation in the solution, where your zinc metal is placed in the anode. To keep the solution electrically neutral, there must be some means for the zinc cations to migrate out of the anode half cell. So para hindi siya mag-remain deposited sa solution, kinahanglan may means siya nga i-transfer sa pihak and for anions to migrate. Similarly, the reductions of the copper 2+ at the cathode removes this cation from the solution, leaving an excess of the sulfate anion in that half cell. To maintain electrical neutrality, some of these anions must migrate out of the cathode half cell. Kung sa anode, ang naga-migrate class is the cation, take note. Sa anode, where oxidation occurs, it's the cation that migrates. Now, allow me to speak in Ilonggo para maintindihan nyo. Kunti may zinc metal, kamuaging butang sa copper sulfate solution. As the chemical reaction proceeds, ang imo nga zinc metal laga-deposit sa imo nga solution. Ang matabo, mas nagadamo positive siya. Hindi na pwede, kinahanglan makatransfer siya. So, ang ginobra, gipa-transfer siya sa pihak. May agyan siya nga mag-transfer sa pihak. Na anong matabo kung i-transfer naman mo to sa pihak ang cations nga zinc plus 2 cations halin sa anode, i-transfer mo to sa pihak. Di kunti mas mag-ano na karon, mag-less na ang imo nga anions. So, it's here, must be some means for zinc cations to migrate out of the anode half cell and for the anions to migrate. Similarly, the reduction ng copper sa pihak, di ba ang imo copper sa pihak sa cathode, gen-reduce ta into copper 0. So meaning, mas madamo na ang negative subong. Removes these cations from solution, leaving an excess of SO2 anions in the half cell. So ang isa naga-positive, ang isa naga-negative. E paano tani siya address? So kinahanglan may ma-transfer ged. So in this case, in fact, no measurable electron flow occurs between the electrodes unless a means is provided for ions to migrate from the solution from one half cell to the other, thereby completing the circuit. Now, I will share a new screen. That way I can illustrate to you in terms of a drawing. Now, later on, there will be a video that will be shown to you as well. Okay? Para mas clear. Okay, this thing you need to fully understand. Wait, class, ha? Okay. I will share a new page, whiteboard. Okay. Okay, let's say, for example, I'll have here one. We call this the electrode. I have here. This is my zinc metal. Another electrode here. It has a solution, and this is your copper. Okay, 2+. Okay, we said that this one is oxidation. The zinc loses away electrons. So oxidation from 0 to +2, it loses electrons. In the process, this zinc here, the zinc cations increases in number. So zinc 2+ cations increases in number. I use the sign in the solution. So nagadamo ang zinc cation sa solution. So meaning, ini siya nga solution subong ang anode, this na anode of yours, where oxidation occurs, becomes more positive. Okay? Now, hindi na pwede kay kinahanglan gani neutral ang duha ka electrodes as mentioned already. Now, diri sa sininga side, ang kakatabo naman yang imo copper 2+, ining copper metal mo nga na place sa solution, gains electrons, and it is converted into neutral copper atom or element, no charge already. So this is your cathode, and this is where reduction occurs. Reduction in the sense that copper accepts the electrons. In the process, anong kakatabo di class? This solution of yours becomes more and more negatively charged. So in this case, mas naga-greater negative siya. Iniya naga-greater positive kay tungod nga ang zinc nag-transfer dire, nahimo siya more positive because from the neutral zinc nahimo na siya zinc plus 2, ini nag-negative. So paano na siya i-address? So there has to be a transfer of ions in that case. So it's being addressed by the what we call they call this the salt bridge. Okay. There has to be transfer of ions. That way, ang ginsubra niya di ihatag niya dito. By the way, class, the transfer is from here to here. So, your zinc, by the way, let me erase this one. Okay, this is not the arrow. Or I will just conclude later. So you would see, or I'll ask you probably para mabalang ko kung ka-intindi ka mo. So your zinc positive here, this becomes more and more positive, and this one becomes more and more negative. For this not to happen, nga ini siya magpuro positive, kag ini magpuro negative, I have an initial question to everybody. Hopefully somebody can answer. What should be the transfer in here? Should zinc be transferred from this side to this side? That way, ini nga negative, mag-neutral. Kag dason ang subra dire, hindi na magsubra kay gin-transfer niya di. Or, it's the other way around. The sulfate here, the negative charge in here will be the anions, rather in this side, should be transferred on the right side. That way, this will not become more and more negative, and the positive charge in here will be neutralized. What do you think is the process of transfer? Is it like this? Or like this? Okay, who can give, you can place your answer in the chat box. We'll see who will give the right answer later in the course of our discussion. What will be the transfer of ions here? Will the cut ions from the left side, from the anode, transfer to the right side, the cathode, or is the other way around? The anions from the right side transfer to the left side, which is the cathode. So isa lang ang maisog mag-answer. So cathode to anode. What about? So John Mark also said from right to left. Oh, duha lang? What about the rest? What do you think will be the transfer? Is it right to left or left to right? I will not answer it now. We will check later and you will know ang iban cathode to anode ni. So right to left, right to left. May isa nga naghambal, right to left. May ara, left to right. Isa, right to left, right to left. Okay, sige. We'll go back to that later and see whether you answered it correctly. But the goal of this salt bridge class, the goal of this salt bridge in these two electrodes is to keep the balance of ions in the two. Kaya hindi pwede nga magdamo. Lalo siya nga magdamo kay ma-deplete ini karon ng iyamas. Nga ini magdutay ang positive hasta nga mag-net negative charge siya. Hindi man na pwede. So it has to be balanced out. Okay? We'll go back to this page. I'll go back to where we are in our discussion a while ago. So where is that one? Okay. All I could see is my weight class. I can see any more. There you go. Sige. So new share. Here we are. So we go back to this. So for the voltaic cell to work, the solution in the two half cells must remain electrically neutral. Okay, that's the goal. Okay, so I mentioned already, there has to be a connector, and that connector is what we call as the salt bridge. It's referred to as the salt bridge. I'm sure this is not something new. A salt bridge allows ions to migrate. So wala man yan naging specified diri sa sentence kung anong ions ang migrate and maintain the electrical neutrality of the solution. The salt bridge consists of a U-shaped tube containing an electrolyte solution such as sodium nitrate. So your electrolyte solution present in the salt bridge is sodium nitrate, whose ions should and will not react with other ions in the voltaic cell or with the electrodes themselves. So kung ano ang ara nga solution sa salt bridge, by the way class, ang salt bridge nga solution, it's a form of a gel. Kaya karon kung pupo ano gina siya, do liquid, pag tabuli siya, ano ng term sa English, when you put it upside down into your solution, the entire thing inside your YouTube, which acts as your salt bridge, will be poured down into your solution. So it's most of the time in the form of, it's here, it's a form of a paste or a gel. Okay, so the electrolyte is often incorporated into a paste or gel so that the electrolyte solution of sodium nitrate does not pour out when the U-tube is inverted. Hindi siya maula. As oxidation and reaction proceeds at the electrodes, ions from the salt bridge migrate into the half cells, cations migrating to the cathode half cells, and anions migrating to the anode half cell to neutralize the charge in the half cell reactions. Whichever device is used to allow ions to migrate between half cells, and ions always migrate towards the anode and cations towards the cathode. So actually, you could see here that your anions is from the, where is the anions? There is an excess of anions in the right side. So it has to be transferred to the anode. So you could see here, anions always migrate towards the anode. So transfer to sa anode, and cations migrates towards the cathode. In terms of electrons class, where is the electron coming from in the first place? Diin nagahalingga ni ang electrons? The electrons came from where? If it's the flow of electrons that we are following through, the electrons came from where? Is it coming from the anode or the cathode? Chat box? It's coming from the anode. Very good. It's coming from the anode because in the anode, you have the oxidation reaction. And in the process, electrons are given away. So the transfer then of the electrons will be from the anode to the cathode. But in terms of migration of ions, specify ko ni, emphasize ko ni, in terms of migration of ions, it's both from right to left or left to right. Wala sang sala. Nga aman, because anions migrate from the right to the left, cations migrate from the left to the right. But as to, if you are just asked as to where electrons are coming from, electrons coming from the left, and that's from the anode towards the cathode. So that answers the question I gave a while ago. So electrons, if we specify flow of electrons, it's supposed to be from the left to the right, as I have accidentally mentioned also a while ago. But in terms of migration of ions, it's both. Anions from right to left, cations from left to right. So as you could see in here, in our galvanic cell or in our voltaic cell. So in these voltaic cells, actually, class, you have some form of a voltmeter here that measures the electrical potential, which we'll be talking in a little while, existing between these two electrodes that produce the electricity, the electrical energy that will be utilized in whatever form that will be utilized for. Okay, now I will proceed. Notice in particular, muna ni siya, electrons flow from the anode through the external circuit to the cathode. Because of this directional flow, the anode in a voltaic cell is labeled with a negative sign because that's where your electron is coming from. And the cathode is labeled with a positive sign. So take note of that. We can envision the electrons as being attracted to the positive cathode from the negative anode through which it came from. And its migration is through, again, the external circuit, or the what we call as the salt bridge. Without the salt bridge, class, your the half reactions that occur in the two separate beakers or electrons will just reach to a point na wala na sang bilin kay gin-consume na sang solution ang metal, or ang solution probably naglighter na kay tungod nga ang metals present in solution nagtapik na siya sa metal strips or something like that, or the anions from the solution already adhere to the metal strips that was placed into it. So in that case, if they stand alone, the reaction is not that something that we call spontaneous. Kinahanglan i-connect sila para ang reaction is spontaneous. Now, if you connect the two, then that's where electrical energy is produced. And how do we measure that electrical energy production? It's measured in the form of what we call the cell potential, our voltaic or galvanic cell potential. Okay? Now, oxidizing agents pulls the electrons, while reducing agents pushes the electrons. So you can picture it. The zinc is being oxidized, and the one pulling the electrons from the zinc away to neutralize itself is the copper. Why? What's the purpose of the copper? From its +2, it needs to convert itself to the neutrally charged copper metal. So that's the purpose. So oxidizing agent, in our case, in our example, is copper. So it pulls the electron from the zinc, while reducing agent pushes the electrons. So the push or pull, which serves as the driving force, is called the cell potential, or E of the cell, or also called the electromotive force. The cell potential, or the electromotive force in physics, or the EMF. Now, common unit for the cell potential is the volt. A volt is equivalent to a joule of work measured per coulomb of charge. Take note of this anyway. You have encountered this in physics. A volt is a joule of work per coulomb of charge. Your work here has a unit of joule, and your charge has a unit of coulomb. Now, the standard hydrogen electrode serves as the reference of all other oxidations that are compared to, and thus we say that for our standard hydrogen electrode, this is its standard. So this does some kind of degree symbols, meaning standard. Its cell potential is 0. Okay, the standard cell potential of the hydrogen electrode is 0. This one indicates standard state. So the degree, somehow a degree symbol indicates the standard state at 25 degrees Celsius, 1 atm, and take note of the concentration of the solution, 1 molar solutions. Okay? So standard na siya, basta amo na siya nga condition. Now I move on. Interrupt me if you have any questions. So the total cell potential this time, if you want to measure the cell potential, is the sum of the potentials of each of the electrodes. So for the reaction in this one, where zinc is being oxidized and copper being reduced, the standard cell potential is given as the sum of the two half reactions or half electrode reactions, standard as well. So the conversion of copper cation to copper, and the conversion of zinc metal to zinc cation. Okay, you add the two standard potential of the half cells. That would be the total cell potential. Now, specific values of different cell potentials may be found in tables. So you have here a table, and usually expressed in reduction form. So actually, class, makita mo di sa table o reduction na siya tanan. Hindi rin lang nga part asta. Di na siya asta. Asta rin diyonan. Reduction because you can see in here that your originally, by the way, this one, yeah, reduction because from the originally neutral fluorine, this fluorine atom, you have the acceptance of 2 electrons, so reduction, and it produced the 2 fluorine anion. So these are all reduction half reaction until this part here. For hydrogen, it's neither being reduced or neither being, in this case, class, you could see that it's really being reduced, but as to its standard potential is said to be 0. Okay? Standard cell potential for nitrogen, for hydrogen, where all of these reactions are being compared to. So these are all being reduced. Now, what this is for the reduction reactions. In here you have this one, you could see this is 0. This one is for the reduction of nickel, okay, from the nickel cation to the nickel metal, okay, atom. And then you have here the cations wherein we add the electrons to make them all neutral charge. So this is also reduction. If your reaction class is opposite of this, let's say for example, it's actually there's an example below. If opposite of this, then you have to place here the negative of that particular reaction. So in the case of the copper 2 plus to copper and the zinc to zinc 2 plus, for the copper 2 plus, you see this? Your copper is being reduced. So this is your standard electrode potential for copper. Now for zinc, your zinc is being oxidized. But the way it's written here, class, where is zinc? The zinc is being reduced. So if it's the opposite of this, it would be the negative of this one. So that is why you have it positive. So 0.34 minus minus, so it becomes plus. So it's plus 1.10. So since this reaction of zinc metal converted to zinc cation is the opposite of this one, as I said, then you will have to add to this one the 0.34, the negative of this, because you need the opposite of this one. So that would be 0.76, giving you a total cell potential for this reaction, for this spontaneous redox reaction, copper, where is this one? Copper 2 plus zinc forming zinc 2 plus copper is this one, 1.10 volts. So there's no need for you to memorize this. Anyway, you'll be provided with this. Or if you're not provided with this, you can have this one Googled and you will have an equivalent reduction half reaction potentials. Google will give you even a more complete table than this one. Probably this is not the entire thing. Okay, so you can refer to that from time to time. There's no need to memorize all of these values. Anyway, they are like values which you can easily read out from tables, just like any other value that we take also from tables. Now, before I proceed, do you have any question here as to calculating the overall standard cell potential for a particular redox reaction? None. So you need this class, huh? You need this one. And for you to be able to get the total cell potential. Okay. Now additional notes on the thing about electromotive force and standard cell potential. The more negative is your cell potential, more easily electron is added. The more negative is your E standard value, the more electron is easily added to it. More easily reduced and better oxidizing agent. So it's a good oxidizing agent if its standard potential is negative. If it's more positive, then I think it would be in mathematics, it would be the corollary of this one or the inverse of this one. So more easily electron is lost in this case. Because it becomes more positive, then it's more easily oxidized and it's a better reducing agent. Okay, for more positive standard electrode potential. The strongest oxidizers have the most positive reduction potential. So stronger oxidizers, those that are responsible for the oxidation of the other metals in solution, have the most reduction potential. The strongest reducers naman have the most negative reduction potentials. Ang reducers, most negative reduction potentials. The greater the difference between the standard potential of the anode and the cathode, the greater the voltage of the cell. Mas nagadako ang diferensya between sa standard electrode potential, mas nagadako ang diferensya sa standard electrode potential sa isa ka cell, half cell, or electrode compared to the other, mas nagadako ang voltage ng sina nga cell. So, mas dako siya sang voltage nga mas dako siya sang voltage nga ihatag. Now, before I proceed to this one, any question, I'd like to show to you a video that will complement what I've discussed regarding electrode potentials and voltaic and galvanic cell. Nuclear chemistry is a different topic. So before I go to this, I'd like to show to you a video. You have any questions? Okay, so let me just wait guys, ha? Check ko lang. Okay, let me just share my screen. What you could see in here, it's from YouTube, is the concept of the reaction that occurs in each of the electrodes that brings about the production of an electromotive force when these two electrodes are connected already. So please listen. Let me know if, let me check, okay, full volume. Let me check class. Excuse me. Stop share pa ano. So para mabatian nyo din ang discussion. Too much? Okay.
Wala sa sound, miss.
Oh, sorry. You can't hear it. Wait. You cannot hear the sound.
Hindi, miss.
Oh, wait. Dali lang din class nga. Wait lang class Wait lang din. Stop share panel. Why? Hmm. Share sound. Audio. Na hindi siya mabatian. Hindi lang kasi automatically dyan. Okay, let me check ha if this will work already. I did something on the setting. Hindi ko lang na siya pag-ianan ho na. Let me know if you can hear it. Can you hear it?
No, miss. No, miss.
Can you hear?
No,
No,
miss.
miss.
Bakit? Wait lang. I need help. Wait ka sa. I will stop share. I can give you a 5-minute break para may break ka mo. Stop share ko anay. I'll ask help from somebody here who might know how to do this. Okay? Kaya lang good class. So you have a 5-minute break. We see each other 2:40. Okay.
Wala audio, miss.
Miss, doon audio, miss.
Yes.
Nadulang audio, miss.
Pero mabatian ko ba lagi hapon? Ganyan na tula lang siya pero una may audio siya.
Feeling ko, miss, kung mag-record ka kasi lecture, miss, gadula.
Okay. So hindi ka mag-record. Is-post ko na lang ang record ha. Okay.
Try lang natin, miss.
Kaya i-share ko na lang ni ang link sa YouTube para sa wala disubog. I-stop ko ang recording ha. Okay, so let me just let me know if you can hear my voice, so if you can see what I'm sharing. So we are now on nuclear chemistry. So it will talk about the mass number, the atomic number of a particular element. Okay, in here we represent an element as X, so that's the symbol of the element. And the atomic number of that particular element is the number that you see written on the left bottom part. And the mass number is written on the upper left corner. Now, you know this already since chemistry high school that the atomic number simply represents the number of protons. This should also be the same as the number of electrons if your element is not in an ion form or if it's not charged, it doesn't have negative or positive number. So your atomic number automatically represents the proton and electrons as well for a neutrally charged atom. Your mass number on the upper left corner is the sum of the protons and the neutrons in your atom. Okay, so atomic number Z plus the number of neutrons will give you the mass number. For the commonly known particles, so let's say for example, we have the proton represented as the P. It has an atomic number of 1. So you have here the Z1 and the mass number A, which is 1. Okay. Then this particular proton is can be also represented by the hydrogen atom. So an atom which has an atomic number of 1 and a mass number of 1. Now the neutron on the other hand has an atomic number of 0. It doesn't have any it has 0 for this one because in the first place it's a neutron, so it doesn't contain any proton. And its mass number, since it does not contain the proton, is automatically its number itself. So neutron 1. Okay, so mass number is 1, atomic number is 0. Now, for your electron, this is how it's represented. So, an atomic number of -1 and a mass number of 0. Or it's represented by the beta particle. The beta particle. So, -1 for the atomic number and a mass number of 0. For the positron, another particle, it's +1 for the atomic number and a mass number of 0. This one could be written also like this. So your positron, you could see here, is the electron. Positron is the electron. You could see it in here. So the electron symbol, it's represented as an electron, but rather its charge is positive. Daw pareho lang di siya gyapon sa electron mo, kaso ang charge diri negative. This one is positive. And could be represented as the beta particle, but instead of having a negative charge, a negative number for the atomic number, which is -1, it's now +1 in here. Both electron and positron have a mass number of 0. Okay. As for the alpha particle, if the proton can be represented by the hydrogen atom, the alpha particle is represented by the helium atom. Atomic number of such is 2 and mass number is 4. And this alpha particle, the helium, can be represented, of course, by the alpha symbol. And we have 2 here for the number of protons and 4 for the mass numbers. Now, how do we balance nuclear reactions? So we're now talking about nuclear chemistry, and what we're balancing here is not the number of electrons, is not the number of atoms of each of the elements present, but rather the number of protons and neutrons in a particular nuclear reaction. So since this is nuclear chemistry, we'll be talking about nuclear equations. Now, how do we balance nuclear equations? So I will proceed. Just interrupt me if you have something to raise, a concern that you need to be raised. Conserve, the first step, rather class, is to conserve the mass number A. So the sum of protons plus neutrons of the products of your nuclear reaction should be the same with the sum of the protons and neutrons in the reactants. So in this side, if you look at the mass number, the total is 236. 235 plus 1 is 236. So the same thing should be true on what is written on the right side. So 138 plus 96, you see this coefficient for the n here, particle, and since it's 2, so you multiply this 1 by 2. So this is 98 plus, so this is 98 plus 138, that would be 236 all in all. So the sum of the mass numbers in your nuclear reaction for the products and reactants should be equal. In the same way that we make sure that the mass number should be equal for the products and the reactants, it should also be the same with the nuclear charge. That is the atomic number, the number written on the lowest leftmost portion of the symbol of the element. So the sum of the nuclear charges in the products must equal the sum of the nuclear charges in the reactants. I think this is self-explanatory. So in this side, on the left side, you have a 92. So in this side here, you should have an 80 and a 92 as well. This is 0, so 2 times 0 is still 0. And that's it. So if you would be asked to balance a nuclear reaction, just balance the protons and neutrons and the protons also. So you will balance the mass numbers and the atomic numbers of the products and the reactants. Now, in this example, you will be able to apply the concept of having to balance the mass numbers and the atomic numbers principle, which is basically illustrated in the two examples here. So let me go down here on the example. So polonium with the mass number of 212 decays by alpha emission. So meaning polonium gives off alpha particle. Okay, or that's your helium atom. Okay, write the balanced nuclear equation for the nuclear decay of polonium. Please check if it's really polonium. I'm not sure if it's really polonium. Let me check, ha. Give me a few seconds. Polonium. Its symbol is it really named polonium? Polonium is PO. Yeah. Okay, so it's PO. Just want to make sure because this is being recorded. Okay, where was I? Here. Now, if an alpha particle is a simple helium atom, so helium atom or an alpha particle, so your polonium with an atomic number of 84 and a mass number of 212 will be written as the alpha particle that it's going to emit, meaning it should be in the product side already. And by the way, you can also write it as this one, alpha with a 2 and a 4 in here on the left side numbers, plus a certain atom. So if polonium gives off an alpha particle and decays into a different atom, what is that particular atom? So in here, for you to know this atom, this X atom, you need to, of course, balance the mass numbers. So 212 minus 4, that should be 208. So we're looking for an X element which has a mass number of 208. Then 84 minus 2 should be 82. So it should have an atomic number of 82. And that particular element in which your polonium decays into, in which it also emits alpha particle, is your plumbous or plumbic atom, or we call the lead atom or the lead atom. Okay. Now 208 for its mass number and 82 for its atomic number. Okay. So if you would be asked what is the difference between an ordinary chemical reaction from a nuclear reaction, what should your answer be? So this is a nuclear reaction depicting the decay, the atomic decay or the nuclear decay of polonium, emitting an alpha particle and the lead atom. So the difference of the ordinary chemical reaction with the nuclear reaction primarily is, number one, we don't balance in the nuclear reaction the number of atoms. We don't balance here the number of atoms. What we balance here are the mass number and the atomic number. As simple as that. Okay? Now, below, you have here the comparison of a chemical reaction and a nuclear reaction. Let me check. Okay, igo pa man siya. So when you speak of a chemical reaction, the usual chemical reaction that we're talking about, so atoms are rearranged by the breaking and the forming of chemical bonds. So let me explain this. When the sodium metal, it's metal N plus, and your chlorine anion, Cl negative, stands alone, your sodium metal, let's say its property, if you have performed this laboratory experiment in high school, if your sodium metal is thrown into, let's say, a beaker which has a very little water or even more water, or is thrown into the zinc where you perform your experiment, it will pop. It will make a popping sound. It will keep on exploding until your metal, your sodium metal is consumed already. So that's the chemical and the physical characteristic of your sodium. It's a metal, and when it's reacting with water, it will explode. Lupok-lupok na siya, gadagan na ganyan ng estudyante, kumaga muna siya kung ma-accidentally dagdag siya sa may tubig. Because that's how its behavior. Stand alone, that is your sodium. Now, when we speak of chlorine, an ion coming from chlorine gas, chlorine is a highly poisonous gas. So very poisonous, and it's a non-metal. Now, these two properties of the component elements or atoms, sodium and chlorine, is very different when these two already combined into, let's say, for example, the compound we call sodium chloride. Now, you may wonder why, how come that a metal, sodium, and a chlorine gas, which is poisonous, when they combine already to form a compound sodium chloride, it's something that is very essential in our diet. So I recall this example because you may wonder why nga ating ginagamit siya magluto. If sodium chloride is missing in what we are eating, it doesn't taste any good at all. It's so bland. Whereas if they stand alone, metal, sodium stand alone, and chlorine stands alone, they are not beneficial to us. Why? Because the explosive ang sodium metal stand alone if it reacts with water, or if it could be used by in a different manner because it's a metal. Your chlorine is very poisonous. So this fact is due to the arrangement or the rearranging of the atoms. So your sodium atoms and your chlorine atoms, when they fuse already and they rearrange themselves, the identity of the sodium and the chlorine atoms are preserved. Ang sodium gina siyang atom. Ang chlorine man na siyang atom. Nothing happened to it. Their identities are preserved. But rather now, when they fuse, it's in the manner in which their atoms rearrange, that way they form what we call the sodium chloride, that the behavior of the two existing substances, sodium and chlorine, if stand alone, changes. So it's different when we say that sodium already changed or chlorine already changed. It's different. What I'm trying to say here is when these two elements combine, the sodium and chlorine atoms did not change at all their identity. Wala na yan nag-change ang identity ni sodium kag chlorine atoms. However, by the manner of their rearrangement so that they'll form sodium chlorine, that compound that produces these two now has a different set properties than the original atoms. But it doesn't mean that the properties of the two elements are changed already. It's just that due to the rearrangement of the atoms, the behavior is already very different. So through the rearrangement and the breaking of bonds, elements or compounds behave differently than their previous elements stand alone. So in this case of chemical reactions, only electrons in atomic or molecular orbitals are involved in the breaking and the forming of bonds. So only electrons in atomic or molecular orbitals are involved in the breaking and forming of the bonds. The electrons that you see class in, let's say for example, sodium, it has one less electron than proton, and then chlorine has more electron than the proton. So these are the electrons that we're talking about here are the free electrons. The atomic or the molecular orbitals electrons are the ones that are involved in the chemical reaction. So the Na plus and the chlorine minus, when they fuse together, makes one neutral compound. So the excess electron of the chlorine atom is gained by the sodium cation. That way it neutralizes itself. So the compound that is produced is already neutral. Now, reactions are accompanied in this case by absorption or release of relatively small amounts of energies. Okay, this is in the case of the usual reactions that we're talking about. The energies that are being needed for the reaction to occur or the energies that are released in the process of the reactions are small amounts of energies. That is why the scientists are harnessing already the energies that is produced when you break an atom, because that's tremendous amount of energy. But if we just talk about the transfer of electrons from one atom to another, not much energy is released in the process. But there is a release, but not comparable to if it's the atom itself that we disturb or we break it. And that's already the process of nuclear fission or nuclear fusion. Now, rates of reactions are influenced when we speak of chemical reactions by temperature, pressure, the concentration, and the presence of the catalyst. I think everybody knows that when we speak of a catalyst, it hastens the chemical reaction or the rate of the chemical reaction is increased when we have the presence of the catalyst. The opposite of which is the inhibitors. So if the catalyst increases the rates, the inhibitors decreases the rates of the chemical reaction. So these four are actually factors that affects the rate of your chemical reaction. Now, what about nuclear reactions? Now, in the case of nuclear reactions, elements or isotopes of the same elements are converted from one to another. Elements or even isotopes of the same elements are converted from one to another. Who can tell me what's an isotope here? Anyone? It's a fundamental thing that is learned in high school. I can even remember it as my chemistry teacher then taught us. What's an isotope?
Two or more atoms, Miss.
Two or more atoms of what?
Two
They
or
are
more atoms with the same atomic number.
Miss.
But they differ in their position.
Almost there, almost there. Atoms of the same atomic number, but
Different numbers of neutrons.
so if they have different number of neutrons, what can we say about their mass number?
Different man.
Different. Salamat, may nag-interact sa akin. So when we speak of, but the way it's defined then when I was in high school, and even until now, nothing changed with the definition, is this. When we speak of atoms, they are atoms of the same elements, having the same atomic number, but they differ in their atomic weight. So if they differ in their atomic weight, their mass number also changes. Didn't you know that your mass number came from the atomic weight? Didn't you know that? Do you know that your mass number is your atomic weight rounded off to the nearest whole number? Do you know that? Or it's only now that you know about it? I hope some already know it. Ang inyo bala mass numbers, ang inyong atoms or sa inyong elements, iyan na atomic weight, nga again, whole number lang. Try to check your periodic table. The atomic weight of a particular element when rounded off to the nearest whole number or kung ano man ang pinaka-nearest whole number to it is its mass number also. So when we speak of isotopes, these are atoms of the same elements, pareho nga element, the same atomic number but different atomic mass or atomic weight. So in the case of nuclear reactions, these elements or these isotopes of the same elements are converted from one form into the other. Like you have a carbon 14 can be converted to carbon 11 to carbon 12 or something like that. So damo-damo siya. The same element kinaistoryahan ta but they differ in their atomic weight, but the same atomic number. Now, in the case of nuclear reactions, number 2, protons, neutrons, electrons, and other elemental particles may be involved. Or shall I say, as we mentioned a while ago, in ordinary chemical reactions, we balance atoms. Okay, we make sure that oxygen, hydrogen, and other elements present in the left side and the right side of our chemical reaction should be the same in number. That's the ordinary chemical reaction. In nuclear reactions, what we balance are these particles, protons, neutrons, and electrons, and other elemental particles that may be involved in your nuclear reactions. Now, number 3, reactions are accompanied by absorption of release of, take note, tremendous amounts of energy. Normally, we produce tremendous amount of energy when we disrupt the atom itself. Kung ang atom, naging mismo yung imo is LAN, like for example, in the decay of polonium, it decayed into the lead atom, and in the process, it emitted the alpha particles. It produced tremendous amount of energy. It produces energy which has a value a lot greater than the normal energy that is being released or needed for ordinary chemical reactions. Okay? Rates of reactions normally are not affected when we speak of nuclear reactions by temperature, pressure, and the catalyst. So, wala tanay gina-consider ang temperature, pressure, and catalyst when we speak of nuclear reactions. Now, we go down. So now we go to, if you don't have any questions here, we go down to nuclear stability and radioactive decay. Radioactive decay actually was illustrated in the example here of the polonium atom decaying into the lead atom. Now, a nuclei is considered stable. So the nucleus of the atom is considered stable when the number of neutrons and protons are almost the same, or when the ratio of the neutron to proton is close to unity. Now, based on your basic knowledge of chemistry in high school, we know that our nucleus is nuclear. It's neutral in charge. Why is it neutral in charge? Because it has the neutrons in it. By the way, your electrons are in the electron cloud and your nucleus has what particles? Ano nga particles sa nucleus ng atoms?
Neutron means.
Neutron lang. Tinang proton niya.
Ara man means.
Kabalan, kung gibala kong estudyante, kung bala katulog na or wala na sa ilang computer, kay when I talk of something that is, mawalan ko lang na after ko nahambal ko na, when I talk, what did I say? It's wrong when I say that the nucleus contains only the neutrons. It contains both the protons and the neutrons, and it's wrong to say that it's neutral in charge because it's in itself is positively charged because of the presence of the protons. Okay, your nucleus is positively charged because of the presence of the protons, but it contains both neutrons and protons. So if my students are already asleep, I know that they are not reacting already. So if I say something wrong, which I realize after I have said it already, that they are asleep. Okay, so in this case of a nuclear, so a nuclear is considered stable, the stability of the nucleus, it's considered stable when the number of protons and neutrons it has, take note, the neutrons and protons it has are the same. If they're not really the same, then it's close to unity, meaning the almost one naman la ang ratio ni neutron kag ni proton. Then your nuclei is said to be stable. What happens when the neutron to proton ratio deviates from 1? As in, hindi na siya negligible ang deviation sang ratio ni neutron numbers kay proton numbers sa nucleus. A nuclei becomes unstable and therefore is considered radioactive. Your nuclei, when it is unstable, is radioactive. But when it is stable, it's non-radioactive. So the greater the value of the ratio of the number of neutrons to protons deviates from 1 million, let's say ang ratio niya 2, 3, 4, 5, the more radioactive is that particular element. Okay, in order for the nuclei to achieve stability, it may need to increase or decrease its neutrons or protons, or even both, until it reaches a point where the N to P ratio is close to 1, if not really equal to 1. So your nucleus, the nucleus of the atom needs to give away the neutrons or the protons with the goal of making the ratio of the number of the two in the nuclei of the atom almost 1, if not equal to 1. Such is achieved, so the giving of the protons or the neutrons to gain stability for a nuclei is achieved through undergoing what we call radioactive decay, which includes beta decay, positron decay, electron capture decay, alpha decay, and spontaneous fission. So any of these 5 in here. It could be beta decay, positron decay, electron capture decay, alpha decay, or spontaneous fission. Your atom may utilize any of these radioactive decay routes. That way, it will gain stability. Okay? Amo na ang pwede niya obrahon. Pwede siya mag-undergo beta decay. positron decay, electron capture decay, alpha decay, or spontaneous fission with the goal of achieving neutrality. Why should it achieve neutrality? So that that particular atom will not be anymore radioactive. Now, if the neutrons to proton ratio is too large, ano matabo kung tama naman kadako? The nuclei usually undergoes beta decay to achieve nuclear stability. On the other hand, when the neutron to proton ratio is too small, the nuclear undergoes positron decay or electron capture to achieve stability. So, if too large ang ratio ni N to P, it should be beta decay. If it's too small, then it can undergo positron decay or electron capture decay or electron capture. Sometimes it would need a series of several and different types of decays for the nuclei to reach stability. The different types of decay happens as follows. So, we'll be discussing here the different types of decay. So, kung dako-dako, beta. Kung gamay lang, positron or electron capture. Now, beta decay. A beta particle is simply an electron, stated already a while ago. In beta decay, the radioactive nuclei releases a beta particle or an electron and its corresponding daughter nuclei. So in beta decay, your radioactive nuclei releases a beta particle or an electron and its corresponding nuclei, daughter nuclei. So in this case, you have this example for beta decay. Okay, you have carbon 14 here, an isotope of carbon, because you also have carbon 11 or 12. Atomic number is 6. So it has here beta decay. So a while ago when I presented to you the particles, these are the particles, review. So this is your beta particle, the electron. Okay. Beta symbol, -1 here in the atomic number and 0 for the mass number. If I change this to positive, it's positron. Positron or electron capture. Now, we go back to what we have mentioned. We have the example there. So you can see here that when your carbon, your isotope of carbon, carbon 14, undergoes beta decay, the atom that it produces is nitrogen. Why? Because dapat niyang ila sining atomic number mabalance ta. Kung 6 na dire, ano nga number ang i-add mo sa -1 para mag-6? So that would be 7. And you find for that element which has an atomic number of 7, and that's your nitrogen. As for the mass number, both your carbon and your nitrogen has more or less the same mass number. Your electron or your beta particle has a mass number of 0. So the decrease in the number of neutrons by 1. So naggamay ang number of neutrons mo by 1 in this case. Now, we go to this one, potassium. Potassium. So you have beta decay here. So what number will you add to -1 to make it 19? So that will be 20. The 20. So from an original potassium atom, now you produce the calcium atom. So you have your mass numbers here, which is 40, left side and right side. And you have your atomic number here, 19, and this is also 19. So in here, you have increase of the number of protons by 1. Now, I'd like to ask you a question. How was this determined though? It says here, decrease of the number of neutrons by 1. Di niya niging kwa. This one, in here, there's an increase in the number of protons by 1. Where was this taken from? And you see here, you have your neutron. So that's your particle, your neutron. Let me go back. This is your neutron. And you see this on the product side of the neutron, you have the proton and the electron. So this is your neutron. Proton plus electron, this becomes 0 and this one is 1. I'd like to ask, ano ang basis ini? If you're still with me, what's the basis for the decreased number of neutrons by 1 in the first example and an increase of protons by 1 in the case of the second example? So I am not alone. So let me see. Okay. Marion says in the atom part of beta means in the atom part of beta. Is this what you're referring to, Marion? In the atom part of beta, to identify increase or decrease siya. To identify increase or decrease siya in the atom part of beta. Can you explain it further? In the atom part of beta. These are all beta. So how do you, why we say that in here, there's a decrease in the neutrons. In here, there's an increase of the protons. Anybody who can answer aside from Marion, si Marion maniguro gyapon. Because the neutron gets converted into proton. The neutron gets converted into protons. We don't convert neutrons to protons, are we? The particles, our nuclear particles, are preserved in the process, in the course of the reaction. They are only being transferred, but we don't change their identity. Just like when, ato ba lang example ko sa sodium kag chlorine, si sodium kag chlorine atom, siya mo ginaiya identity, why gina siya galain. Gali ang behavior na sang compound which comprises the two is very different than the elemental atoms because of the rearrangement of the atom. So there's another answer here. Sa atomic mass ka-atomis. John Mark. So atomic mass of atom. Sa atomic mass of atom, John Mark, in the case of nitrogen, its atomic mass is 14. In the case of calcium, its atomic mass is 40. So how do you explain this increase in protons and in here decrease of neutrons? Neutron splits into proton and an electron. The neutron splits into a proton. The neutron splits into a proton and an electron in this case. Marian says the neutron splits into a proton and an electron. Marian, if there's a splitting of the neutron into proton and electron, how does it explain this one? How does it explain the decrease of the neutrons and the increase of the protons by 1 in the first and in the second example?
Sa electron, miss.
Sa electron, who is this, by the way? Who is this?
Awero, miss.
Hero. Sa electrons, where did you look at it? Di mo nakita ang electrons. I don't see any electrons in the reaction.
Sa beta, wala miss na, hindi na siya, miss.
Okay. So beta. So sa beta electrons, then, what about? Pareho man na sila tanan may electrons. The first one has the emission of a beta particle. The second one is also emitting beta particles, so beta decay. How do you explain this? Okay. Okay, one more shot and then I'll proceed. Kaya hindi ko pag-answeran. Changing of proton sa neutron, miss. Changing of proton to neutron. Si proton na change to neutron?
Ang atomic number niya mas ma-change into ano mas?
Ang atomic number ni proton ma-neutral?
Atomic number as 6 mas ma-change into 7.
Atomic number nga 6, miss. Mahimo siya. Actually, from 6, it went to 7 here for carbon. Anyway, I will leave this as an assignment because I don't want to discuss this now. I want you to do your part. Whoever is able to give me an answer that is plausible, acceptable, next meeting, that will be credited to you as points in the next quiz. So that will be +5 in the next quiz. May dali lang. Last na itong hamba kung may last ba din. Kay ang and neutron miss will be transformed into proton. Amo na nagbuhin ang neutron and nagdugang ang proton. Diyan, sa neutron miss. Your neutron will be transformed into proton. Amo na nagbuhin ang neutron and nagdugang ang protons. If this answer of yours, John, is correct, in this case, deribla sa duwa ka example, kaya gina-ask ko ya, ini. Nga you can say here that there's a decrease of the neutron and in here, there's an increase of the proton. If I will refer to your answer, to your reasoning here, nga konsakto, magina siya ha. Let's say for example, it's correct. You're saying that this electron of yours, your beta decay, came from 1 neutron. So nag-decrease ang neutron kay tungod of this one. This one, how do you explain this? Increase naman yes ang proton. Why is there an increase of protons by 1? Same reaction? Same reasoning? I will not explain. Yes, yes? Please, no miss. No miss. Jan. Sige be, Jan. Explain, Jan. You have your mic, Jan. Para mabalance, miss.
I thought, Miss, sa decrease number of neutrons and increase number of protons is sa ang duwa na Miss ka factor is sa isa lang ka ano na Miss ka form ka equation.
You mean these two simultaneously together is for one reaction only? Is that what you mean? If neutron isotope lang ang change, if proton ang element na change. Okay. I cannot get an explanation that is possible that everybody that anyone who is silent would understand. Nucleus emits a beta particle. This changes happen. The atomic number increases by 1. If your nucleus emits a beta particle, your atomic number should never increase. Kaya ang atomic number is referring to the protons, number of protons. Okay. Sige, I get it. Because in the process of the emission of the beta particles, you're also producing the proton. But look at this class, dali lang gida, one thing na lang. Your proton here, let me go back to the particles, is this one. Okay, 1 atomic number, 1 mass number, equivalent to the hydrogen atom. And this probably is the one that your classmate is referring to. Where ako beta decay pa lang ako. Ay, where is it? Okay, this one. Now, next meeting, we will discuss this para maka-continue ko ha. We will just continue. I will ask for somebody who can give me the plausible explanation to this one in here, to what it refers to, and that would be added +5 in the next quiz. Hindi na magsulat sa chat box para ka-proceed ako. That way, everybody will get to participate, especially in this lengthy discussion that we have now. I will not explain that part, okay? I proceed to positron decay, okay? Positron decay. A positron is a positively charged electron. In positron decay, the radioactive nuclei releases a positron and its corresponding daughter nuclei. It releases a positron and its corresponding daughter nuclei. So an example of a positron decay is this. Still carbon, an isotope of carbon, this time 11. So you have a positron decay in here, a positively charged electron, and the atom that is produced in the process is the boron atom. So atomic number 5 and mass number of 11. And you have here another example, your potassium undergoing positron decay, producing the argon atom. So 18 plus 1, that would be 19. So there's not much to balance anyway in the mass number because your particles here have 0 as the mass number. And again, we have this one, an increase of the neutrons in here by 1, a decrease of the number of protons by 1. So nagdamo ang neutrons diri isa, nag-decrease ang protons diri isa. Okay? Now if it's electron capture decay, in electron capture decay, the radioactive nuclei captures an electron which results, an electron which results into a daughter nuclei. So instead of writing the electron on the right side or on the product side, you are now going to write it on the reactant side because it's being received. Excuse me. So your argon undergoing electron capture, it captures an electron, will produce your chlorine atom. In here, there's an increase in the number of neutrons by 1. Now here in your iron, if it accepts an electron, captures an electron, it will produce the manganese atom. 25 in atomic number and 55 in mass number. And you have the corresponding general equation for an electron capture. Okay, this is your proton, this is your electron, you produce a neutron in the process. This one is a proton undergoing positron decay, producing the positron particle and your neutron. Okay, now what about alpha decay? So we have electron capture. Now this is alpha decay. This is the fourth type of decay. The alpha particle is equivalent to the helium atom. You know this already. In alpha decay, the radioactive nuclei releases an alpha particle or a helium atom and produces a daughter nuclei whose mass number and atomic number is 4 and 2 less respective than the mother nuclei. And the atomic number is 4 and 2 less respectively than the mother nuclei. So you have here the alpha decay of polonium, and it produces this particular helium atom, so an alpha particle, and it produces an atomic number whose mass number and atomic number is 4 and 2 less respectively. So naibanan ang imong mass number and atomic number by 4 and 2 respectively in the mother nuclei. So subtract 4 here, subtract 2 here. Amo ning ginanamin niya. Okay? Whose mass number? So 200 minus 4. And atomic number minus 2. Now, this is your parent nuclei and this is now your daughter nuclei. Okay? In here, you have a decrease of neutrons by 2. You have a decrease of the number of protons by 2 in this one particular reaction. That's for alpha decay. The last type of decay is spontaneous fission. Radioactive decay. So there are 5, right? Mentioned a while ago. So this is the last. What's spontaneous fission? So spontaneous fission involves the spontaneous meaning non-induced na siya splitting of the nucleus of the heavier elements into 2 nearly equal nuclides or fission fragments and the simultaneous emission of more than 1 neutron on the average. So we know when we speak of fusion, nag-fuse sila, nag-become 1. When we speak of fission, nag-divide. So in this case, spontaneous fission. or non-induced splitting of the nucleus of heavier elements into two nearly equal nuclides or fission fragments, and the simultaneous emissions of more than one neutron on the average. So in this case, class duha ka neutron ang iya again emit, and you have two equal nuclides, indium ni siya. Okay, two nuclear nuclides of indium. So you have 98, you have 49 times 2, that's 98. For this side here, you have 98 for the atomic number, and this is 250, 252. So this is also balanced. So this is for the atoms to gain nuclear stability. So para mag-stable ang atoms, kinahanglan niya mag-undergo sining 5 ka-types of decay. So we have beta, positron, electron capture, may alpha pa to sa baba, and then we have this last, which is regulating alpha, spontaneous fission. Okay? Now, let me see kung ano pa siya kalawig. Almost done. Now, notes on nuclear stability. So certain numbers of neutrons and protons are extra stable. So N or P equal to 2, 4, 20, 50, 82, and 126. Meaning, siniklas, kung may number of neutrons or protons nga among niho, they are extra stable atoms. Like extra stable numbers of electrons in noble gases. Ini siya extra stable atoms which has this number of neutrons or protons. Amo ni nga number. In the case of noble gases, these are the number of electrons: 2, 10, 18, 36, 54, and 86. So this time we are looking into the number of electrons when we speak of the stability of noble gases. But when we speak of the stability of just the standard other elements other than the noble gases, and these are the numbers of the protons and the neutrons. Now, nuclei with even numbers, take note of this, nuclei with even numbers of both protons and neutrons are more stable than those with odd numbers of neutrons and protons. So if you're going to proceed later on in your physical chemistry, you will study this in details regarding the corresponding numbers of protons and neutrons that will tell you that your atom will be stable or not, or what's the possible type of emission for a particular atom for it to gain stability. It will consider this number of protons. But nonetheless, class, basta even siya ang protons and neutrons, mas stable din na siya kaysa sa odd. Now, all isotopes of the elements with atomic numbers higher than 83, all isotopes of the elements with atomic number higher than 83 are radioactive. So if you have several isotopes, and since they have the same atomic number, they only differ in their atomic weights. Ato ang atomic weights nga higher than 83 will be more radioactive than the other isotopes. So this particular principle, class, is applicable when you speak of isotopes. Okay? Atoms of the same atomic number but different in atomic weights or atomic in their atomic weights or mass numbers. Now, all isotopes of I forgot the names of these elements. Kindly look in your periodic table. The TC and the PM are radioactive. So you can look at them in the either in the inner transition or transition part of your periodic table. Now, the last part here will be nuclear binding energy. Tapuson ko na lang para at least ma-free ka mo sa Thursday. Okay? You just read on the rest here and check on the answer to my question a while ago. Now, nuclear binding energy. What is this? Nuclear binding energy. Nuclear binding energy is the energy required to break up a nucleus into its component protons and neutrons. So the nuclear binding energy, as an example here in the case of the fluorine atom, will be in the process of its nucleus breaking into the proton and the neutron atoms. We have 9 here for protons and 10 for the neutron, giving here a 19 for the mass number and 9 for the atomic number. So this is how your fluorine atom breaks up. How the nucleus of a fluorine atom breaks up. So how do we account for its binding energy? We go back to Einstein's formula. Delta E is equal to mc squared. Okay? So in here, you have the 9. The delta M, you need to determine first. So for the delta M, you have 9. This, I think, is for the proton times the proton mass plus 10 times the mass of the neutron minus the mass of the fluorine atom. Take note, class, that since your fluorine atom has only 1 here on this side, so this is only 1. But since you have 9 and 10 here for the protons and the neutrons respectively, their masses should be multiplied by these coefficients that appear on the left side of their symbols, as written in the nuclear reaction. So 9 times the mass of the protons plus 10 times the mass of the neutrons minus the mass of the fluorine atom. So this is the mass of the proton, class. This is the mass of the neutron. And this is the mass of your fluorine atom. Your delta M is 0.15887 atomic mass units. So AMU is atomic mass units. So if we'll determine the delta E, the delta M that we got in here, it's pre-calculated and substituted to the formula. So you have 0.1587 times C squared. So what is C, by the way? You know what is this C?
Speed of light, Miss.
Kala ko ang iban mo ay gyapon kagahod. So this is speed of light. Is this the speed of light? Are you sure? The 3 times 10 raised to 8? Speed of the C squared in the MC squared. Is it speed of light? Are you sure? It's the speed of, ano na tabo sa mga chemical engineers to be? The speed of, it's not light, speed of sound. The C here is the speed of sound. The 300, times 10 raised to 8, that's 5, 6, 300 million. I think, class, this is 3 times 10 raised to 5 only. Let me check, ha? Kasi ako na ang na-amnesia. Let me check. Just give me a few minutes. Okay. Miss Ali stands corrected. It's the speed of light. So local speed of sound, which is 300,000 only. So it should be 300 million. Let me check, ha, para sigurado. Basi nagka-typo error ako for the C. Okay. Speed of light. Ginag-google ko siya, class, para sure. Wait. Britannica. Wala pa gid ang may naka-dispute sang E equal to mc squared ni Einstein until now. Meaning the great minds now still agree with this guy. Okay. Gin-round off yan na. Amo na gina-check ko gid ang speed of light nga value. Na hindi ko siya. Better make sure rather than giving you. Although there's nothing wrong with not memorizing this one because it's not meant to be memorized. You can just find this in Google or you can find this in encyclopedia. In our time, hindi uso si Google, so we really have to cram and look for it in the encyclopedia. Okay, thank you for that, John. Okay, ang actual nga values ng speed of light is 299,792,458 meters per second. Thank you to Google. So then it was rounded off in this case. That is why at first I disagreed because it doesn't look like it's the speed of light because it was rounded off. So in this case, this is your speed of light. I hope you can still see the original document that I'm sharing. And this is the answer to the delta E. Okay, the binding energy, the nuclear binding energy. So in this case, it's negative 1.43 times 10 raised to 16 AMU meters squared per second squared. Look at this class. It's really stipulated. It's really specified here that it should be negative. Why? Because it's amount of energy released. I think your physics or your chemistry have emphasized that whenever it is released, it should be negative, and if it's absorbed, it's positive. So if you wish to convert the atomic mass units to kilograms, so this is the corresponding conversion, 6.022 times 10 raised to 26. And you can also convert the corresponding unit after you have changed the AMU to kilograms. You will have now a set units of kilogram meter squared per second squared, and that could be converted to joules. Our answer here for the delta E in this particular example, in the splitting of the fluorine atom, this is a fluorine atom that we have, in joule is 2.37 times 10 raised to negative 11 joules. Again, it should be negative because it's released energy. Okay? Now, if you're going to convert that to kilojoules, so it's negative 1.43. Okay, conversion na siya na negative 1.43 times 10 raised to 10 kilojoule per mole of fluorine. So kilojoule per mole of fluorine atom. This is your answer now, 1.43 times 10 raised to 10 kilojoule per mole. The binding energy per nucleon is the binding energy divided by the number of nucleons. In our case here, our number of nucleons, the particles present in the nucleus of the atom, or simply the sum of the protons and the neutrons, you have 10 and 9. So this is the total binding energy, but the binding energy per nucleon should be divided by the total number of particles present in the nucleus. You take the sum of the protons and the neutrons, and that should give you 1.25 times 10 raised to negative 12 joule per nucleon. Again, nucleons, the sum of the protons and the nucleus of our atom. In this case, that's our fluorine atom. Okay, this ends this particular part on the topic nuclear energy and electrochemical energy. I will edit this part of the lesson in our Canvas. That way you get to see the video that I'm supposed to be sharing with you. And then in your spare time on Thursday, you can go over it again and listen to it. That way, what I have explained, if it's not that polished, it would be polished by the explanation in the video. Okay? I go back to your assignment. Nothing that should not be submitted, but I will ask somebody to give the answer to this. Why this one? But this one is started here. Why this one? Why this one? Is this referring to this one or is this referring to this? So that's your question. That's the question that you need to answer. If you're able to answer that next meeting, the first one to answer will get a plus points in the quiz. Any question? Or the first one who can give me an answer that is basic, fundamental, and easily understood by your classmates. Not nga, I'm sure kamo ka-intindi kamo, pero gusto ko sa explanation nga klaro, nga maka-intindi ang inyong classmate, hindi ako, hindi ang inyong classmate when you explain it. I will stop sharing now. Any question? Your chemical engineering teachers class will attend the convention this week. So our convention will start online lang man. Wednesday, it will end on Friday. So all of your chemical engineering professors will be giving you tasks to do. So on Thursday, your task is you read again the part that we have discussed this afternoon and think about the answer to the question I gave a while ago. Now, there is a question in the chat box. Miss, may quiz sa Thursday. Wala gani. Ang obrahon nyo sa Thursday, basahon nyo liwat ang gin-discuss ko. Kag pangitaon nyo ang sabat sa ginpamangkot ko. Kung kay sino explanation ang clear para sa akon nga maintindihan sa inyo classmate, then I will accept it and you gain the plus point. So somebody still wrote. Okay, you reserve your answer, Daniel, next meeting when I talk to you randomly kung sino ang makahatag sa sabat sa akon pamangkot. Okay? Para at least may kita, hindi siya monologue, hindi na siya nga ako lang the istorya. Okay? Now, there will be exchanges of ideas. Thursday is your asynchronous time, your SDL. You know what SDL is? Self-directed learning time. So, kung matuon ka mo, sa inyo na. Kung hindi ka mo magtuon sa inyo, magyapon. Okay? Now, what happens next week? Tuesday next week, I will give you, of course, a quiz on Module 2. So, the coverage will be the entire Module 2. But before kumagatag quiz class, we will have review for 30 minutes. Ma-review tanay. So, from 1:30 to 2, we will review. I will listen to your questions, base may questions ka mo, and I will listen to your answer to the question I give you to research. Then your quiz will start 2 o'clock. At most, it will only be until 1 hour and a half. So 3:30, you should be done by then. Then Thursday in your asynchronous time, I will leave you a recorded video on Module 3 already. A recorded discussion on Module 3. You will see it also in your Canvas because before I discuss it, it will already be in your Canvas made available for you. Okay?